The last case is when we have an even power on our tangent and an odd power on our secant. So m is even and n is odd. In this case, what you'll do is you'll use tangent squared is secant squared minus 1 to write everything in terms of secants, and then you'll use identities or integration by parts. And then also, these two integrals you can take as a given. The integral of tan x is the natural log of absolute value secant x plus a constant, and the integral of secant x is natural log secant plus tangent absolute value plus a constant. So let's look at an example. So we want to integrate secant cubed x. So what we're going to do is we are going to break this integral up into secant x times secant squared x dx. And then we're going to do integration by parts. So we need u and dv and du and v. So you want to pick u, so it's got a simpler derivative. Well, derivative secant is secant tangent. That's not simpler, but derivative secant squared, that's going to be power rule for functions. That's going to be worse. So I probably want to pick u equals secant. And then dv, easy to integrate. Well, integral of secant, well, that's right here. And it's not, a nice formula either. And then integral secant squared, oh yeah, that's tangent, right? Antiderivative secant squared, because derivative tangent secant squared. So it makes sense to pick dv equals tan x dx. I'm sorry, secant squared x dx. V will be tan x. So v here is going to be tangent x. Du there will be secant x tan x. So we want to do uv, the diagonal product, minus integral v du, integral of the last row. So this is going to be uv secant tan, secant x tan x, and then minus integral v du, which is going to be secant x tan squared x, dx. Give ourselves a little bit more room here. There we go. And so we've got that secant x, tan x, and then minus integral secant x. And then we want to write everything in terms of secants using tan squared is secant squared minus 1. So we swap this tan squared out for a secant squared x minus 1 dx. So this will now be secant x tan x, and then minus, let's multiply this in. So this will be integral secant cubed x times secant minus 1 minus secant x dx. And then we can take the integral of each piece there. So this will be secant x tan x. Let's go ahead and distribute our minus sign. So minus secant cubed and plus secant. So minus integral secant cubed x dx. And then double negative there, plus integral secant x dx. So now let's look at our two sides here. So we've got the secant cubed on the left, on the right, secant tan, minus integral secant cubed, x dx, and then plus integral secant. So what we want is we want this. We want the integral of secant cubed. We'll notice we got another integral secant cubed over here with the negative sign. So these two are like terms. We want to move this one over on the left as a positive. So we have a positive secant cubed and another positive secant cubed. That's 2 integral secant cubed. So there's that idea of having the integral on both sides and collecting it like it's a single quantity. And it is. What's left here is secant x tan x. And then plus our integral of secant. And what's integral of secant? Well, it's natural log secant plus tangent plus a constant. So ln absolute secant x plus tan x. And then plus our constant. And now we just need to divide both sides by 2, or if you want, multiply by 1/2. So these guys cancel, and our integral of secant cubed dx is 1/2 secant x tan x plus 1/2 natural log absolute secant x plus tan x, and then plus our constant. Now you might be wondering, why didn't I multiply the 1/2 there, times the c? Well, this is an arbitrary constant, so if you multiply it by 1/2, it's still arbitrary constant. So the arbitrary constant absorbs multiplications. So notice this is the same setup we had when we did the integral of e to the x cosine x. We had the integral on the left side, and then we had an expression involving the same integral on the right hand side. We brought those over to the left and combined them like terms and solved for what was left. So there's that idea again.